Hello everybody. My name is Zeyu and this is Humphrey. We're from Morphing Lab, Carnegie Mellon University. So we have a big team in this project. I want to especially mention Guanyun as our first author and Lini as our advisor. They take a lot of effort in this project, and the other team members are contributing different aspects in this project. So today, on behalf of them, we're here to present you 4DMesh, standing for 4D printing morphing non-developable mesh surfaces. So 4D printing is a fabrication concept introduced as 3D printing plus transformation over time. So in some scenarios, we're observing 4D printing as more space-saving and economical than conventional machining. And to some extent, it's also a material and time-saving than 3D printing, since it will help to eliminate some support materials and support structures. So our group of Morphing Lab has investigated 4D printing in different scenarios, including edibles, gadgets and toys made of thermoplastic, and now 4DMesh, aiming at larger items that have some structural demands. So long story short, 4DMesh is using single material and maker version FDM printer to produce comparably large-scaled items with non-developable mesh surfaces. So to make it clear, the non-developable surfaces, meaning surfaces that maintains non-zero Gaussian curvatures locally. To make it intuitive, you can interpret it as surfaces that cannot be flattened without shrinking or stretching. So for instance, on the left-hand side, we can see a kirigami egg shape, which is a developable approach towards that shape. And in 4DMesh, we're aiming at a non-developable approach, which is one step closer to the right-hand side shape. And the basic non-developable surfaces are cone shape and saddle shape. So with those, we can involve more arbitrary and organic form factors in our design. So additionally, I want to mention we adopted mesh structure instead of a continuous surface because the mesh structure maintains enough structural strength while saving us a lot of printing time and material. And also, it will help to enable double curvature by eliminating some encounter forces inside the structure. So looking at 4D printing in different scales, we can see that 4DMesh is introducing a pipeline to produce comparably large items, and specifically, it provides an inverse design tool to process non-developable surfaces. So in order to approximate a 3D surface that is given, we designed a pipeline starting with the software that flattens the 3D surface into a flat mesh configuration with some local geometric information. And after we get that, we can plan out the printing path and print it out with the 3D printer. And then we submerge it into hot water, and it will morph into the target shape that we desire it to be. So it becomes some artifacts like this. So following this pipeline, I want to introduce you to our digital workflow, our flattening algorithm, and we'll include some detailed discussion about how the performance is in our technology. So starting with the workflow. Firstly, in our software, we give user a choice between two algorithms that we implemented to flatten the given 3D surface. And after you do that, the software will automatically flatten the 3D surface into a flat mesh configuration containing some local geometric information, either shrinkage or bending angle. And finally, the software will output a G-code file to guide the 3D printing. So using this tool, the users can adjust the algorithm and rasterization parameters and receive some visual feedbacks real time. And on the fabrication side, we're using Stacker S4 printer, which is a maker version FDM printer, similar to MakerBot with a comparably larger printing bed. And in terms of filament, we're using only one kind of material, which is PLA, and this is an off-the-shelf PLA filament. More detailed information is included in the paper. You're more than welcome to check it out. And the mesh configuration we're printing out consists of joints and beams. Since we want to diminish the negative influence the joints provides towards the morphing process, we actually printed them with a lower infill rate so that it will be as flexible as possible when the transformation is taking place. And the beams consist of actuators and passive blocks. Since, as I mentioned, we're only using one kind of material, so if you see this kind of representation later on, the colored bars are not another kind of material. They're just printed in different printing patterns. So they're the actuators. and the white ones are the passive blocks that will not do shape change during the transformation process. And after we print out the mesh configuration, we submerge into hot water to heat it up and trigger the transformation. Since we're scaling things up, as I mentioned, the gravity will become an issue. So the artifacts will sink to the bottom of the tank and interfere the transformation. So in order to compensate that issue, we actually added sugar to the water to increase the water density so that the artifacts will neutrally buoyant in the water. So after we're clear about the fabrication process, let me introduce you to our flattening algorithm. As I mentioned, we actually implemented two of them based on two different kind of actuators. One is the shrinkage-based actuator, and the other is the bending actuator. So they both have pros and cons, and users are allowed to choose which one to use according to their specific scenarios. And starting with the flattening algorithm with the shrinkage-based actuator, we're actually distributing different shrinkage ratio in the beams in the mesh configuration. So that just, for instance, if you're distributing more shrinkage ratio on the outer line and less in the middle, the whole mesh will pop up in the middle to become some shape like this. So by distributing different shrinkage ratio distribution, it can help us to achieve different curvatures, both locally and globally. So the shrinkage-based beams are printed with shrinkage actuator and passive blocks. So as the printed parts will shrink along the printing traces when heated up, so the shrinkage actuators are printed along the longitudinal axis of the beam, and the passive blocks are perpendicular to that. So here we give a formula to calculate the actuator length in each beam. So on a higher level, with a given fixed beam length, the longer the actuator is, the more the beam will shrink. So we're modulating this ratio to control the overall shrinkage of each beam in the mesh. And we got a lot of technical details that we cannot cover in this presentation. So here we're giving you an outline of the shrinkage-based flattening algorithm. So the input is a 3D CAD surface, and we first render them into triangular mesh, and then simplify it with quadratic edge collapse decimation to prevent the mesh to be overdensed. And then we flatten the mesh with least squares conformal maps with eigenvalue approach. And by comparing the length difference between the previous two mesh, we can get the shrinkage ratio on each beam on the mesh configuration, so that we can section out how long the actuator should be in each beam, and then print out the configuration and let it morph to be the target shape. So following this workflow, we're actually generating several artifacts as applications for this method. So taking the lampshade in the first row as an example, once we get the 3D shape, we render it and remesh it to be a simplified mesh and flatten it, and then maintain the local geometric information, which is shrinkage ratio in this scenario, and then plan out the printing path, print it out, and trigger it with hot water, so it becomes a lampshade like this. And another artifact I want to mention in this method is the chair seat. So this chair seat is too big to be printed in our printing bed. So we actually sectioned them out into two parts and flattened them and fabricated them separately and glued them back together with epoxy. So it becomes a chair seat like this.
And now I'm going to talk about our bending-based actuator and the flattening algorithm developed for it. So our bending-based actuator actually has a similar structure to our shrinkage actuator. We're still using a single material, but we're structuring the printing paths differently. In this scenario, we substitute certain layers of the actuator with constant blocks that has perpendicular printing paths. By doing so, we create an isotropy in the material shrinkage such that when heated, the beam will bend toward the side that has actuators. And we can control the bending direction of the beams by positioning the actuator block on either side of the beam. Similar to our shrinkage actuator, we can control the overall bending angle for each beam by modulating the length of our actuator. And again, there are a lot of technical details we can't cover in this presentation, but they are detailed in our paper. Please check them out there if you have questions. And here we're giving you an outline of the flattening algorithm. So we developed our flattening algorithm for bending actuators based on the Chebyshev net algorithm, but we made some modifications. First of all, during the meshing stage, we first extend the surface to make it into a larger one, and then we mesh it and crop the mesh edges to fit to the original, to reconstruct the outline of the original input. And during the flattening stage, to better approximate the bending actuators and the surface, we convert the straight edges on the mesh into arcs. And then we deploy Chebyshev-Nash algorithm on the plane again to derive a planar mesh. And then but this time we are using the length of the arcs to, instead of using a uniform length for the edges. And then based on the angles of the arcs, we assign actuators to each individual edge. And then we generate G-code files and fabricate artifacts. And leveraging the advantages of our bending actuator, we design several applications. First of all is this full plate. This full plate is concurrently curved on both directions of the surface. And with our bending actuator, we can actually control each individual beam to curve on a specific direction. So here's a picture of the final outcome. And as you can see, this full plate is curved on both directions. And our algorithm adopting Chebyshev-Nash is especially good at processing input surfaces that has a rather rectangular outline. And also we designed an armor set. Specifically, this shoulder armor has a large bending curvature along one direction. It's bending more than 180 degrees. And with our bending actuator, we can actually achieve this drastic curvature. And here's a picture of the armor set. In addition to the shoulder armor, notice how well the chest piece is fitting to the body curvature of the wearer. This is especially desired in costume designs. And now, after showing both our flattening algorithms, let's make a comparison of them. Each of our flattening strategies has their own design spaces and unique benefits. For instance, our bending-based actuators can process both cone shapes and saddle shapes and has a larger achievable surface curvature. But on the other hand, our shrinkage-based actuator better preserves the outline of the original input, and additionally, it is structurally stronger. We have also probed the idea of combining both of our flattening strategies together to produce artifacts. So here we show a helmet. The shell of the helmet is designed with our shrinkage actuator to achieve higher structural strength, and the face shield is designed with our bending actuator to achieve larger bending angle. And we have also tested the structural strength of our 4DMesh using a mechanical compressive load. And our advisor also decided to sit on it to test it by herself. And yes, there was a pass or fail moment for us. And at the end of our presentation, we would like to share with you our vision in 4D printing. We have a vision to create a 4D printing ecosystem leveraging smart materials. In this vision, software and design tools is an important part to interface designers to these materials. And these tools and softwares will also handle the fabricational aspects. The fabricated artifacts can be packaged flatly, saving packaging space, and consequently reducing shipping costs. The artifacts can be transported on-site and triggered on demand. Some of the materials, such as the thermoplastics we're using in 4DMesh, are recyclable, hence creating a circular ecosystem. The designers in our team are excited about 4DMesh for several reasons. First of all is its customizability to create ergonomic shapes in haste. And also, non-developable services provides a unique aesthetics. And since we're pushing things in a larger scale, we're also thinking about the possibility of producing larger scale structural components. And me, myself, as an architect, is imagining an architectural practice in which we produce houses in factories and transport them on-site and trigger them into their functional states. Let's see, at the end of our presentation, we would like to acknowledge Wang, CMU School of Architecture, CMU Graduate Student Assembly, and Next Manufacturing Center. Thank you for listening to our presentation. We're now open for questions.
Cool. Hi, Laura Olberg, University of Calgary. Cool. It's thermomolding. Who doesn't love it? I actually want to ask more about the structural qualities. So you're basically introducing compression and tension into the structure itself. Mm-hmm. So I'm wondering how that affects some of the more durability, long-term viability of this sort of approach, whether or not it would last for a couple days or a couple years. So what's the longer-term vision of how these hold up over time?
So the chairs we have designed lasted for roughly a month before someone sitting on it and eventually break it. And we have observed the fracture patterns of the chairs. So yeah, actually they're pretty strong against compression. But the weak point actually is the seams due to the FDM printing process. So the structure is actually weaker against tension.
Hi, Dan Ashbrook, University of Copenhagen. I'm curious how the thickness or the width of the beam affects the properties of the material. Does it change how much it can bend? Does it change the strength?
Yes. So yes, the geometry of the beams will affect the transformation performances. And in this paper, we are basing our beam parameters on the thickness. We base it on commercially available plastic chairs to ensure its structural strength. And the width, we decided our width based on the nozzle width of our printer, and also we ran some preliminary simulations to check basically how wide the width of the beams should be. And there's also another factor that determines how wide the beams should be. So because the joints actually interferes with the transformation process of our 4D meshes, so we actually want to eliminate the joints or make the joints as small as possible. And you can imagine that the wider the beams are, the larger the joints will be. So we have to modulate basically between structural strength and transformational accuracy.
Okay, cool. One more question. Does environmental heat affect the final position? So if it gets very hot, will it fold more or collapse?
Yes. So the triggering temperature is actually a tricky thing to select. First of all, you want the temperature to be high enough to allow the artifact to complete its transformation before it cools down, right? And on the other hand, you want the temperature to be low enough to minimize convection in the hot water to have it interfere less with the transformation. So yes, there are a lot of factors that can affect the transformation accuracy and the transformation itself.
But I'm thinking about after it's transformed. So now I have a chair in the room and the heat comes on.
So when triggering the artifacts, we're actually heating the thermoplastic above its glass transition temperature. That is about 60 degrees Celsius. And in room temperature, I can't really imagine there will be a scenario where this is exposed to that degree.
Fair enough.
Yeah.
Thanks.
But yeah, if you blow hot airs on the chair, it will start to deform.
So I have a question, actually, and it's about chairs, which sometimes you want to be really comfy. And it seems that you have structure that not only has to be durable, but you want it to flex just the right amount when you sit in it, for example, not be too hard, not be too soft, be, kind of just right. So in the tools you have, do they give you some insight into the way in which it's going to flex when varying kinds of forces are placed on them?
Well, since we're using POA in this project, so the chair itself is pretty hard, right? And we didn't investigate into the aspect of using soft materials or compliant materials to make the chair seat softer, say. And I suppose that could be included in future works to use composite structures for 4D printing. And in terms of the deformations of the chair, we actually conducted some finite element analysis. And from the results, we think that the chair should be quite comfortable for people to sit on.
Hi. I have a question.
Yes.
So in some of your structures that you showed, the curvature was actually designed in a very unique way. So I was just wondering if there is any geometry constraint. Like, for example, were there any designs that you weren't able to mold the structure to? And like, if you have, it's very hard for me to explain. Like, but okay.
Okay, so actually our bending actuators can, if you have a bending actuator about this long, it can bend more than 180 degrees. But in our applications, the bending angle for each beam rarely goes beyond 60 degrees. So that's why we're not showing that drastic transformation here.
Okay,
Thank you.